Okay, so I posted the exam grades this morning on Blackboard, and the first thing I'm going to do is go over the exam, which is also a nice review of things we've been doing. So exam 2, solutions. Let's see, any questions before I start? No? Okay. So problem 1A, we have the following function. Y equals x plus 7, x squared plus 2 over x minus 2 cubed times x plus 1. And we want to find dy dx by logarithmic differentiation. So we take the log of y. And by the rules of the logarithm, the log of a product is the sum of the logs. The log of a quotient is the difference of the logs. So this is the log of x plus 7 plus the log of x squared plus 2 minus the log of x minus 2 cubed, but a power can be put in front of the log, minus the log of x plus 1. And then when you differentiate with respect to x, the derivative with respect to x of log y, on the one hand, by the chain rule, that's 1 over y dy dx. And on the other hand, by differentiating this term by term, the log of x plus 7 is 1 over x plus 7, plus the log of x squared plus 2 is 1 over x squared plus 2 times the derivative of x squared plus 2, which is 2x, minus 3 over the log of minus 3 over x minus 2. Minus 1 over x plus 1. So if you multiply through by y, dy dx is y times this whole expression. Right? That's the answer. Okay. Any questions about that? No? Okay. Part B, we have the equation x cubed y squared minus the sine of y equals 11. And we want to find the dy dx by implicit differentiation. So when you differentiate with respect to x, what do you get? The derivative of x cubed is 3x squared times y squared plus x cubed times the derivative of y squared with respect to x, which is 2y dy dx, minus, when you differentiate sine y with respect to x, you get cosine of y times dy dx is equal to the derivative of the constant function 11, which is 0. So that's 3x squared y squared plus 2x cubed y minus cosine y dy dx equals 0. So when you solve for dy dx, you get minus 3x squared y squared over 2x cubed minus cosine y, or you can write this as 3x squared y squared minus times minus, this makes this cosine y minus 2x cubed. Any questions about this? Oops. Oh, yeah, good. Okay. Problem 2. We have the function f of t equals cosine t minus sine t, and we want to find the absolute extrema on the interval from 0 to pi. So we're not looking at this function anywhere else, only from 0 to pi. So that means we have to evaluate the function at the endpoints of the interval and at any critical points in the interior. So f prime of t, this is minus sine t minus cosine t. When does that equal 0? That's the same as saying that sine t equals minus cosine t, or sine t over cosine t equals minus 1, which is the tangent of t equals minus 1. And when does the tangent of t equal minus 1? Well, when t is equal to 3 pi over 2 or 7 pi over 2 plus any multiple of 2 pi. But between 3 pi over 4 and 7 pi over 4. And the only value of t in the interval 0 pi is at 3 pi over 4. So we need to consider only the values t equals 0, t equal 7 pi over 4, t equal 3 pi over 4, and t equal pi. F of 0, cosine 0 minus sine 0 is 1. F of 3 pi over 4, that's the cosine of 3 pi over 4 minus the sine of 3 pi over 4. That's minus 1 over root 2 minus 1 over root 2 is minus 2 over root 2, or minus root 2, which is about minus 1.4. And f of pi, cosine pi minus sine of pi, minus 1 minus 0 is minus 1. So we only have to consider these three numbers. Which is the biggest? 1. Which is the smallest? Minus root 2. So the absolute maximum is f of 0 equal 1 at t equals 0. The absolute minimum is f of 3 pi over 2, which is minus root 2, and t is equal to 3 pi over 4. So this is the absolute max, and that's the absolute min. A lot of people didn't realize that you only look at values of the function between 0 and pi. That's exactly what the question is asking, and that's what you have to answer. Okay. Any questions about this? Problem 3, we have the function f of x equals x to the 4th minus 12x squared minus 11x. And we want to find the points of inflection and the open intervals where the function is concave up and concave down. So even before we start, we know roughly what the answer is like, because a 4th degree polynomial, if the leading coefficient is positive, will typically look something like that. So you would expect there's a region where it's concave up and a second region where it's concave up. And in between, it's concave down, and you have inflection points at 2 places. So just from the general shape of a 4th degree polynomial, you know what the answer probably is going to look like. But now we have to find the inflection points and the intervals where the function is concave up and down. So we take the first derivative, and then we take the second derivative, which is equal to 12x times x minus 2. And we set that equal to 0. Oops, minus 24x. Let me do this right. 12x cubed minus 24x. So that's equal to 12 times x squared minus 2 equals 0. And it equals to 0 at 2 places, when x is plus the square root of 2 and x is minus the square root of 2. And if you look at the number line, when x is bigger than the square root of 2, this is positive. So the curve is concave up. And similarly, when x is less than minus the square root of 2, the second derivative is positive, and the curve is also concave up. And in this open interval from minus root 2 to 2, f double prime of x is negative, and the curve is concave down. So we have that the curve y equals f of x is concave up on the open intervals from minus infinity to minus root 2, and from root 2 to infinity. Concave down on the open interval from minus root 2 to plus root 2, with inflection points at x equal root 2 and minus root 2. Okay. Any questions about this? Okay. Problem 4. We have a cubic curve f of x is 2x cubed minus 15x squared plus 25. So we know that a cubic curve generally looks like that. So you expect it's increasing, then decreasing, and then increasing again. Let's see. The first derivative is 6x squared minus 30x, which factors into 6x times x minus 5. So this is equal to 0 when x equals 0 or 5. If we take the second derivative, we get 12x. So the second derivative at 0 second derivative is 12x minus 30. Second derivative at 0 is minus 30. That's negative. So x equals 0 is a relative maximum by the second derivative test. F double prime evaluated at 5 is 60 minus 30, which is plus 30, which is positive. So x equals 5 is a relative minimum. If we look at the derivative, f prime of x equals 6 times 6x times x minus 5, what can we say about this? On the number line, when x is bigger than 5, f prime of x is positive, so the function is increasing. When x is less than 0, f prime of x is also positive because you have negative times negative, and the function is increasing. And if you look at the interval x between 0 and 5, positive times negative is negative. So the function is decreasing. So f of x is increasing on the open interval from minus infinity to 0, union or together with the open interval from 5 to infinity, and decreasing on the open interval from 0 to 5. So these are the open intervals where the function is increasing and decreasing. And this tells you where you have a relative maximum and a relative minimum. Okay. Okay. Questions about this? Okay. Problem 5. We have a rectangular solid with a square base whose surface area is 96. So this is x, the base is square. Let's say the height is y. So the surface area, A, well, the top and the bottom are squares of size x, so each of them has area x squared, and there's a top and a bottom, so 2x squared is the area of the top plus the area of the bottom. And each side has area xy, and there are 4 sides. So that's the area of this rectangular solid with a square base, and we're told it equals 96. If you want to solve for y, you get 4xy is 96 minus 2x squared. So y is equal to 96 minus 2x squared over 4x, or if you divide by 2, 48 minus x squared over 2x. And the volume, V, is the area of the base times the height, x squared y. But this is what y is. So this is x squared times 48 minus x squared over 2x. Let's see, 48 over 2x is 24 over x times x squared is 24x minus a half x cubed. So this is the volume. And we want to find the dimensions of the solid that give us the maximum volume. So dV dx, if you differentiate it, is 24 minus 3 halves x squared. That's equal to 0 when 3 halves x squared equals 24, or 3x squared equals 48, or x squared equals 16, or x equals plus or minus 4. But a negative dimension makes no sense. So x is going to be equal to 4. And what is y? Y is 48 minus x squared over 2x. That's 48 minus 16 over 8. That's 32 over 8, or 4. So the maximum volume arises from a cube with all sides equal to 4. And the maximum volume itself is 4 cubed, or 64. Any questions on this? Okay. So this was an optimization problem, and the last problem was a related rate problem. This is problem 6. So you have a right triangle, x, y, and z, and x and y are changing as a function of time. dx dt is changing, is increasing at a rate of 4 centimeters per second, and the height, dy dt, is increasing at a rate of 3 centimeters per second. So for part A, we want to find how fast the volume dA dt is changing when x is equal to 5 and y is equal to 12. Well, the area is a half the base times the height. So dA dt is equal to 1/2 dx dt times y plus 1/2 x dy dt. dx dt was equal to 4. A half of 4 is 2y plus dy dt is 3 plus 3/2 x. So when x is 5 and y is 12, the rate of change of the area is 2 times 12 plus 3/2 times 5. That's 24 plus 15/2 So that is 48 plus 15 is 63 halves, or 31.2 square centimeters per second. So that's the answer to part A. Right. Part B is find how fast the hypotenuse is changing when x is 5 and y is 12. What is the hypotenuse? Well, you have the Pythagorean theorem. Z squared is x squared plus y squared. And when x is 5 and y is 12, that's 5 squared plus 12 squared. That's 25 plus 144. That's 169, which is 13 squared. So when x is 5 and y is 12, z is 13. So we can either solve the Pythagorean theorem for z, or we can just use implicit differentiation. 2z dc dt is 2x dx dt plus 2y dy dt. Right? Of course, the 2's cancel. So z dz dt, 13 dz dt, is equal to x, which is 5 times dx dt, plus y, which is 12 times dz dt. This is 20 plus 36 is 56. So dz dt is 56 over 13. Okay. So that was the whole exam. Right? Any questions about this? All right. So then we go on to lesson 26. Which is the fundamental theorem of calculus. So this is what allows us to calculate definite integrals very nicely. So what it says is the following. If a function f of x is continuous on the closed interval from a to b, and if capital F of x is an antiderivative of f of x on AB, then the definite integral from a to b of f of x dx is capital F of b minus capital F of a. So this is the really important result in Math 175 that relates an integral to a derivative in a beautiful way. So let's do some examples of using the fundamental theorem. This is example 1 in the text. And the first of the examples is to calculate the integral from 1 to 2 of x squared minus 3 dx. So here the function that we're integrating is f of x equals x squared minus 3. And the antiderivative, capital F of x, that is the indefinite integral or antiderivative of x squared minus 3, is 1/3 x cubed minus 3x. So this is my antiderivative, capital F. And by the fundamental theorem, this is capital F at 2 minus capital F evaluated at 1. When x is equal to 2, this is 1/3 2 cubed minus 3 times 2. When x is equal to 1, this is 1/3 times 1 cubed minus 3 times 1. This is 8/3 minus 6 minus 1/3 minus 3. So this is 8/3 minus 1/3 is 3 minus 6 plus 3 is 0. Oops. See, 8/3 minus 6 minus 1/3 minus, oh, sorry. 8/3 minus 1/3 is 7/3. 7/3 minus 6 plus 3. That's 7/3 minus 3 is 7 minus 9 is minus 2/3. I mean, what does x squared minus 3 look like? That's a parabola translated down 3 units. Parabola looks like this. And we're asking for the area under the curve from 1 to 2. But area above the curve is positive, area below is negative, this minus this. We get a negative number for the area, but that's because, again, we have a plus or minus sign assigned to areas. So the integral is minus 2/3. Any questions about this? Let's do some more examples. Suppose we have the integral from 1 to 4 of 3 times the square root of x dx. We can always take, well, 3 outside. Square root of x. Well, actually, let me just do it differently. Let me calculate the antiderivative. Right, so the antiderivative, capital F of x, the integral of 3 root x dx. That's 3 times the integral of x to the 1/2. That's what the square root is, dx. Remember the rule that the integral of x to the n dx is x to the n plus 1 over n plus 1 for all n not equal to -1, where the denominator would be 0. So here, the exponent is 1/2. This is 3 over 1/2 plus 1 is 3/2. X to the 3/2. That's 2x to the 3/2. That's the antiderivative. So we evaluate this. F of 4 minus f of 1. When you plot x equal 4, let's see, that's 2, 4 to the 3/2 minus 2, 1 to the 3/2. Square root of 4 is 2. 2 cubed is 8. We get 16 minus 2, or 14 as our answer. Now, you do have to know a little bit of high school algebra to do this calculation, but in calculus, we assume you've learned your high school algebra. Another example is the integral from 0 to pi over 4 secant squared x dx. So in order to do this, you have to remember that the derivative of the tangent is secant squared. So the antiderivative of secant squared is the tangent. So this becomes f of pi over 4 minus f of 0. That's the tangent of pi over 4 minus the tangent of 0. And again, you also have to know trig. Tangent of pi over 4 is 1. Tangent of 0 is 0, and 1 minus 0 is 1. All right. So this is a basic calculation that you have to know in Math 175. So here's a homework problem, which perhaps you've done. Compute the integral from 0 to pi of 1 plus sine x dx. So I'll give you a second to do it, and then maybe someone can tell me the answer. As you go from 0 to pi, sine of x looks like that. So 1 plus sine x looks like that. So we're asking for the area under the curve 1 plus sine x from 0 to pi. So this is going to be equal to f of pi minus f of 0, where capital F of x is the antiderivative of 1 plus sine x. What is the antiderivative of 1? Can someone tell me?
X, Professor.
X. And what's the antiderivative of sine x?
Minus cosine X.
Thank you. Minus. So the antiderivative is x minus cosine x. So this is equal to this evaluated at pi, pi minus cosine pi, minus this evaluated at 0, minus cosine 0. Cosine pi is minus 1, cosine 0 is plus 1. So this is equal to pi minus minus 1 plus 1 plus cosine 0, which is another 1. So we get as our answer pi plus 2. Any questions so far? Let's do one more example. Let's try to compute the integral from 0 to 2 of the absolute value of 2x minus 1 dx. Now, in order to figure out, it's very hard to find an antiderivative of an absolute value. So we should really look at this function, y equals the absolute value of 2x minus 1. What does that look like? Well, if 2x minus 1 is greater than or equal to 0, this is 2x minus 1. And if 2x minus 1 is less than or equal to 0, this is minus 2x minus 1, or 1 minus 2x. So in other words, yeah, that's what it is. It's 2x minus 1. And so when is 2x minus 1 greater than or equal to 0? So this is 2x minus 1 if x is greater than a half. And it's equal to 1 minus 2x if x is less than or equal to a half. So if you look at the graph of this function, here's the vertical line, y equal to a half. This is 1 minus 2x for x less than or equal to half, and 2x minus 1 for x greater than or equal to a half. So the graph of this function looks like that. In fact, once you know that, I'm going to solve this problem using the integral, but we can also solve this problem knowing the definition of the integral as an area. Here, this function is always above the x-axis. So this little triangle has area a half the base times the height, which is 1/4. And this triangle has area a half the base, which is 3/2, times the height, which is 3, which is 9/4. So the total area of 1/4 plus 9/4 is 10/4, is 5/2, or 2.5. So we expect when we're done that this is the answer. Okay, that's like a check. But now let's do it by doing integrals. This is the integral from 0 to 1/2 of 1 minus 2x plus the integral from 1/2 to 2 of 2x minus 1. Because this function has different expressions for x less than 1/2 and x bigger than 1/2. What is the antiderivative of 1 minus 2x? Can someone tell me what the antiderivative is, or the integral? What's the integral of 1 minus 2x?
It's x minus 2x to the power 3.
No. What's the integral of x?
It's half x to the power 2.
Right. So times 2 is just x squared. Because you differentiate x squared, you get 2x.
Right.
Let me call that f1 of x. So the integral from 0 to 1/2 of 1 minus 2x is f1 of 1/2 minus f1 of 0. That's equal to 1/2 minus 1/2 squared minus 0 minus 0. 1/2 minus 1/4 is 1/4, which you'll notice is exactly that. And for the second integral, let's say f2 of x is the integral of 2x minus 1 dx. It's just the opposite of this in sign. That's x squared minus x. So the integral from 1/2 to 2 of 2x minus 1 dx is f2 of 2 minus f2 of 1/2. That's equal to 1/2 squared, or 1/4, minus 1/2. Sorry, f2 of 2 is 2 squared minus 2, 4 minus 2, minus 1/2 squared minus 1/2. That's equal to 2 minus 1/4, which is 9/4. Exactly that. And when you add the two together, you get 1/4 plus 9/4, which is 5/2. So that's what it is. So this is the fundamental thing you have to learn in this section, how the fundamental theorem of calculus allows you to compute a definite integral. Now, just as there is a mean value theorem for derivatives, there is also a mean value theorem for integrals, which says if you have a continuous function on the closed interval from A to B, there exists a number C in this interval such that the integral from A to B of f of x dx is just this number f of c times the length of the interval. So if this is A and this is B, and this is y equals f of x, what this says is there's some number c such that if you take this rectangle whose height is f of c and whose base is b minus a, that has the same area as the area under the curve, y equals f of x from A to B. But this statement, which takes some time to understand algebraically and geometrically what it means, that's what's called the mean value theorem. And the proof is very pretty. So suppose we let m be the minimum value of f of x on this interval, little m, and capital M be the maximum of f of x on the interval. Then f of little m and f of capital M. So these are the points where these minimum and maximum values occur. So f of m is less than or equal to f of x is less than or equal to capital F of m for all x in the interval from A to B. So when you integrate with respect to x, you preserve the inequality. But this is a constant and this is a constant. So this says that f of m times b minus a is less than or equal to this definite integral from A to B of f of x dx. It's less than or equal to f of m times b minus a. And if you take this inequality and divide by b minus a, you get f of m is less than or equal to 1 over b minus a, the integral from A to B, f of x dx, less than or equal to f of m. And by the intermediate value theorem, there exists a number c in the interval from A to B such that f of c is equal to 1 over b minus a, integral f of x dx from A to B. And when you rewrite that, that has proven this mean value theorem. There's also something which is many times useful in applications. We want to have the notion of the average value of a function f of x on the interval a, b, and this is the definition, it's 1 over the length of the interval times the integral from a to b of f of x dx. And in a more advanced calculus class, we would actually justify this, but this is actually still a very nice definition and is in a certain sense the right definition of the average value of the function.
Can you put the paper down a little?
Again, everything I'm doing is in the book and legible, so this is really just to make everything more understandable when you study the textbook. So for example, find the average value of the function f of x equals 3x squared minus 2x on the interval from 1 to 4. So it would be 1 over the length of the interval, b minus a, 4 minus 1, times the integral from 1 to 4 of 3x squared minus 2x dx. 4 minus 1 is a third. The antiderivative of 3x squared minus 2x is x cubed minus x squared, and we want to evaluate that from x equal 1 to x equal 4. So that's 1/3 4 cubed minus 4 squared minus 1 cubed minus 1 squared. This is 64 minus 16. This is 1 minus 1. So we get 48 over 3, or 16. So this is just an example of the calculation of an average value for a function. And now we can prove what is often called the second fundamental theorem of calculus. Suppose we let x be a variable and consider the integral from a to x of our function f of t dt. So this is some function of x. And the theorem says if you take this function of x, so this is a function of x, and differentiate with respect to x, you just get back the function f of x. So it's like you start with a function f, you integrate it, then you differentiate it, and you get back the original function. And just to give a sort of a sketch of the proof of this, suppose we let capital F of x be the integral from a to x of f of t dt. Then if you go back to the very beginning of Calc 1, what's the definition of the derivative of a function? It's the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. This is the limit as delta x goes to 0, 1 over delta x. The integral f of x plus delta x is the integral from a to x plus delta x, f of t dt, minus the integral from a to x of f of t dt. If you think of this on the number line, this is a, say a, x plus delta x. If we take this big interval and subtract off the integral just from a to x, we're left with just this. This is the limit, delta x goes to 0, 1 over delta x, the integral from x to x plus delta x, f of x dx. And by the mean value theorem for integrals, this integral is just f of c. For some c between x and x plus delta x. And if we take the limit as delta x goes to 0, c goes to x. So this is always a question on the departmental final. And it's really simple if you remember this fundamental theorem of calculus in its second form. Suppose we have the integral from 0 to x of the square root of t squared plus 1 dt. So this is some function of x. And we differentiate it, we get the function inside the square root sign, square root of x squared plus 1. That's all it is. So we're going through a lot of material in the syllabus in the last couple of lectures in the semester. And it's really worth spending as much time as you can at home studying the textbook and understanding as much as you can of what's going on. And what is a little bit complicated is to try to do something like this. Suppose you have the function capital F of x defined as the integral from pi over 2, but not to x, but to x cubed, something, let's say cosine t dt. And we want to find the derivative. So we could think of this perhaps like this. Suppose that g of u is the integral from pi over 2 to u cosine t dt. And I'll call that little g. I'll call it little f, actually. And suppose we let g of u be u cubed. Well, so f composed with g of u, that's f of g of u, that's f of u cubed, that's the integral from pi over 2, sorry, g of x is x cubed. So g of x, that's f of x cubed, that's the integral from pi over 2 to x cubed cosine t dt, which is capital F of x. So this capital F of x is really this composite function, f composed with g of x. So f prime of x by the chain rule is f prime at g of x, g prime of x. G of x is x cubed, so f prime of x is 3x squared. So this is 3x squared, and f prime, when I differentiate this, I get cosine u. So this is the cosine of u, which is x cubed. So the derivative of this function is 3x squared cosine of x cubed. So this is an example on the text. This is not anything I believe that will be on the final, but if you continue with calculus, it's something that you need to learn. It's looking at this more sophisticated, more complicated integral, where the upper limit of integration is not just the variable x, but some function of x, and you can differentiate that using the chain rule. Okay, well, we'll be spending time on Wednesday and next Monday, which is the last class, with problems that involve the fundamental theorem. But the fundamental theorem of calculus reduces a definite integral to calculating an antiderivative or an indefinite integral. And we haven't learned any general technique for that other than lucky guesses. But there is a method, it's the last item in the syllabus, which is integration by a method called substitution. And it's just translating the ordinary chain rule for derivatives into an integral language. So if you have the composite function f of g of x, and you differentiate that by the chain rule, that's f prime of g of x, g prime of x. This is the chain rule for derivatives. So that means that the antiderivative of f prime of g of x, g prime of x dx is equal to f of g of x. This is an integration rule. Whenever you have something you're integrating, which looks like this is the answer. Another way of writing that is the following, that the integral of f of g of x, g prime of x dx, is equal to capital F of g of x, where capital F of x is the integral of the function little f of x. That is the antiderivative. So let's look at an example of this. This is really a new technique, and it's a skill to develop. Suppose we have the integral of x squared plus 1 squared times 2x dx. So this is really a matter of learning how to see. So if you let g of x be x squared plus 1, g prime of x is 2x. So this is g prime of x, and this is g of x squared. So if you think of f of u as being u squared, this is f, this is the integral of f of g of x, because that would be g of x squared. That's what this is, 2x g prime of x dx. And that's going to be capital F of g of x. Capital F of x is the integral of x squared tx, which is a third x cubed. So this is 1/3 g of x cubed, 1/3 x squared plus 1 cubed. Now, it's always possible to check an antiderivative by differentiating. So let's just check. If I take the function capital F of x equals one-third x squared plus 1 cubed, when I differentiate this, I get 1/3. The derivative of x squared plus 1 cubed is 3 x squared plus 1 squared times the derivative of x squared plus 1, which is 2x. So this is 2x times x squared plus 1 squared, or x squared plus 1 squared times 2x. It's exactly what we started with. So by this miracle of substitution, it works. So here, let's do a number of examples. Suppose we have the integral of 5e to the 5x dx. So what we know is if f of x is the integral of e to the x dx, that's equal to e to the x. We know that. But here we have e to the 5x. But you can think of this as follows. If g of x is 5x, g prime of x is 5. So this is the integral e to the 5x is e to the g of x, and 5 is g prime of x. If I let f of x be equal to e to the x, this is f of g of x, because that would be e to the g of x, g prime of x dx. And by the substitution rule, this is capital F of g of x. That's capital F of x is e to the x. This is e to the g of x, e to the 5x. So that's the answer. That's the answer. Let's see. Let me do some examples from the homework. Suppose we have the integral of the square root of 25 minus x squared times minus 2x dx. So again, this is all in the eyes. Somehow you have to look and recognize. You'll notice that the derivative with respect to x of 25 minus x squared is minus 2x. So if we let g of x equal 25 minus x squared, minus 2x is g prime of x. So this is the integral of the square root of g of x, g prime of x dx. If you let f of x equal the square root of x, this is the integral of f of g of x, g prime of x dx. Now this is exactly in the form of the substitution formula, because if we let capital F of x be the antiderivative of little f of x, which is the antiderivative of the square root of x, or the antiderivative of x to the 1/2, which is 2/3 x to the 3/2. This is going to be capital F of g of x. That's 2/3 x, 2/3 g of x to the 3/2. That's 2/3 25 minus x squared to the 3/2. I'm going to do one more example and then we'll stop for the day. But this is a whole new technique of integrating. And one of the aspects of this technique is you have to be sort of skilled to do this. It's not that there's a rule that always works. It's kind of a skill you have to acquire. So here's another example. In the homework, this is number 17. This is the integral of x squared, x cubed minus 1 to the 4th dx. Now you know that the derivative of x cubed minus 1 is 3x squared. But you don't have a 3x squared here, you just have 1x squared. But if you're just dealing with something that's off by a number, you can always multiply by 1, and you can write 1 as 1/3 times 3, because 1/3 times 3 is 1, so this is correct. And now you see if you let g of x be equal to x cubed minus 1, g prime of x is 3x squared. So this is 1/3 the integral of x cubed minus 1, that's g of x to the 4th power times 3x squared, g prime of x dx. If I let f of x be equal to x to the 4th, this is 1/3 the integral of f of g of x, because that's g of x to the 4th power, g prime of x dx. And this is going to be 1/3 capital F of g of x, where what is capital F of x? It's the antiderivative of little f of x, which is the antiderivative of x to the 4th, which is 1/5 x to the 5th. So this is 1/3, 1/5 g of x to the 5th power. That's 1/15. G of x is x cubed minus 1 to the 5th power. So this is perhaps the answer, and let's check. It has to be the case when you differentiate this, you get back to what's inside the integral sign there. So the derivative with respect to x of 1/15 x cubed minus 1 to the 5th is 1/15 5x cubed minus 1 to the 4th times the derivative of x cubed minus 1, which is 3x squared. 5 times 3 is 15. So this cancels the 15 in the denominator, and we're left with x squared, x cubed minus 1 to the 4th. Exactly what we had to get. So this is exactly the last item in the syllabus. And that's what it is. So we have 2 more classes. On Wednesday, we will do problems involving the fundamental theorem of calculus and the technique of integration by substitution. And on the last class next Monday, we'll go over the practice final exam. I will make sure it's available on the Math Department website, but I will post it on Blackboard, and I will also email it to everybody. So that's really a very good way to prepare for the final exam. Okay. And I will double check with the Lehman final exam schedule and let you know when the final exam is. Any questions before we leave? Okay, hopefully we will all be back on Wednesday. Bye all.